In this video, we're going to begin our study of orbital mechanics. And orbital mechanics really starts with Kepler, who was the first to show and defy really what people believed for hundreds and thousands of years prior to Kepler. And prior to Kepler, people believed that the Earth was the center of the universe. And when Kepler came along, he was able to use the data collected by Tycho Brahe. And after about 10 years of going through the geometry and some number crunching, he was able to mathematically show that the Earth was not at the center of the universe. And so that's one of the really most profound things that came out of Kepler's work. Now, in terms of a timeline, Kepler comes before Isaac Newton. And in fact, Isaac Newton actually used one of Kepler's three laws to help him formulate his law of universal gravitation. All right, now Kepler developed three laws of planetary motion. The first of Kepler's three laws is that the path of the planets are ellipses with the sun at one focus. So this first law implies two things that defied the thought and the logic of the day. And the first thing that it did is it implied that the sun was the center of the universe as the universe was understood at that time. There was no way for scientists to know back in the 1500s that the universe was nearly the size that it is that we understand it today. So, you know, we do say that the sun was at the center of the universe, but to them the universe was really the solar system and then the stars. The other second really important implication of this is that it really flies in the face of Ptolemaic thought. And Ptolemaic thought was that of perfect spheres, that the sun moved around the earth in a perfect circle, and that the planets would move around the earth in a perfect circle. So everything was orbiting around the earth in perfect circles. So if we were to just diagram this very quickly, what we'd see is that the Earth was in the center, and then you would have the sun moving on a perfect sphere, because they actually thought of it in 3 dimensions, not 2, and so that the sun and the planets would be moving in perfect spheres, and so that right here would be maybe the sun going around the Earth, and then you would have another planet going around the Earth, and their model did seem to work most of the time. However, some of the planets, or some of the stars that they saw, I should say, they called planets. And the reason they called them planets is because planet is the Greek word for wanderer. Okay, and so what would happen is in the night sky, as you tracked over a period of days and weeks, what you would see is that one of the planets, it would track normally across the sky like this, but then all of a sudden it would seem to turn back around, go the opposite direction, and then it would continue back on its original path. Okay, and that is called retrograde motion. And basically it's just a reversing of the path. Well, the way they accounted for this in their models was to put an epicycle, which was just another perfect sphere or circle along the path of the planet. So if we say that this planet here was Mars, then Mars would track along this path, and it would be going in this direction. And then when it got to the epicycle, it would follow the epicycle around, and then it would continue back on its original path. And so as you're observing this from the Earth, you would see the planet Mars track in this direction, then it would go back in that direction, and then it would continue on its original course. Okay, now, we know today this isn't the case, but this is what they did. And their models actually got to be quite complex, putting epicycles on epicycles, trying to account for observations which didn't match the theory. Okay, so that might have been the first clue that something wasn't quite right, but their way of handling problems is a lot different than our way of handling problems today. All right, now, Kepler's second law of planetary motion says that equal areas are swept out in equal time. Now I'm going to draw an image of the solar system to help you understand just what this means. Okay, so in our diagram, what you can see is that I've created the solar system, or I should say the sun, and just the path of one of the planets. And maybe we call this Pluto because of how elliptical it is. The shape of all of the orbits for all of the planets and everything going around the sun is an ellipse. Now, just real quick, let's be careful about what an ellipse is. An ellipse is not necessarily egg-shaped, okay? And so I'm going to say this. All circles are ellipses, but not all ellipses are circles. So by saying it's an ellipse, that does include the possibility that it's a circular path. For example, Earth moves around the sun in a very nearly circular path. However, it's not quite circular. It is still an ellipse. So we're always going to refer to it as an ellipse. And some planets have highly elliptical orbits, other planets do not. So let's just assume that this is Pluto. It's forming a highly elliptical orbit, which we know that it does. Now, the planet Pluto is going to, it's moving in this direction, and we'll say that the distance from this point in space to this point in space represents 1 month. That's not accurate for Pluto, but that's what we're going to use for now. And the distance from here to here also represents 1 month. So that's going to be the equal time part of the second law. And if you were to calculate the area bounded here by these green lines, and the area here, those two areas would be of the same size. So that's what his second law is. Equal areas are swept out in equal time. Now, this also carries with it some implications. One is that it hints at conservation, or a conservation law. Conservation is not something that showed up in physics for hundreds of years yet. Okay, so this is still, well before there was ever a clue that we could have something like conservation of energy. But looking back on it, we can see that it hints at conservation. And why is that? Well, it's the whole equal areas in equal time piece. I mean, that's just screaming conservation, yet they had no clue that conservation was even a thing. The other implication is this, and this is the important one to us. This is what would have been important to astronomers, during Kepler's day, and that is that when you're close to the star, the object is moving fast, and when you're further from the star, the object is moving slow. And so it's going to be moving very slowly here. In other words, the arc length, the length of this line, is going to be smaller than the length of this line. Okay? That's all it's saying, that the speed of the planet is actually going to be changing. It's going to be speeding up as it gets closer to the sun, and then when it starts to go in the other direction, it's going to start to slow down. Now, when we get to conservation of energy, we can actually account for that, and we can determine what the speed is going to be at any particular point. Now we get to Kepler's third law. And it's the third law that Newton used to help develop his law of universal gravitation. And Kepler's third law, for right now, I'm just going to write it like this. T squared is equal to kr cubed. And T represents the period for the planet to go around once. R is going to be the distance from the center of the central body. And to Kepler, that would have been the sun, because all of his data was based on the sun. And K is going to be a constant that will be developed later. But I'm not going to do it in this video. And real quick, R, it says distance from the center of the central body. I have to add one more qualifier here because you'll see you're very close in some locations but very far in other locations. And so when we talk about the central body, R is the distance from the central body. This is going to be the semi-major axis. Now, the semi-major axis, well, first of all, the major axis is this one. And the minor axis is this one. The semi-major axis is going to be half the distance from the outer edge of right here. It's going to be half the distance from the outer edge to the center here. And you can take it from either location. You can take it from the part that's closest to the sun or the part that's furthest from the sun to the midpoint. But that's what your semi-major axis is going to be.